All right, purpose of this video is to walk you through the Wien's Law and Stellar Spectra lab, so let's get started on that. Let's begin by looking in the module. If you scroll down, you will find the PDF document that is the template file. You will also see the data file, which is in Excel, and you can tell that because it's got an extension of .xlsx. And then there are the questions here, which is where you will also upload your data file and answer the follow-up questions. What we want to do is we want to download two files here. We want to download the PDF and we want to download the Excel file. So let's go ahead and do that. When I click on that, we're going to open it up. And you'll see up here in the upper right-hand corner, there's a download button and we can download that. So I'm going to click that. Now, my computer will automatically download things to a downloads directory. Yours may be different, but once it's downloaded, it tells me right there. Okay, let's go back and now we can get the Excel file. So I'll click that and it opens and says download. Click the download button, the download link, and then it downloads as well. Now those are put into a downloads folder. So let's go look at that. Here we are in the downloads folder and you can see right here, there's the Excel file and here is the template file. Now the thing that I want to do is I want to copy both of these. So I'm going to select both of them. I'm going to right click and then I'm going to click copy. Now I'm going to go put those in a safe place where I can get to them. And I've created a folder here on my desktop for just this purpose. Okay, and here it is. You can see that the two files are now, the PDF file and the XLSX file are both in my Wien's Law folder. Okay, I'm going to double click on each of these and open them up. Now here I am in the Excel file and you can see this is the data table that I will be filling in. The way to get full credit is you submit this Excel file in the questions section. And you can see there are two data tables. The data tables are always labeled down here at the bottom in these tabs. This is data table 03.01 that we're looking at. If I click on the next tab, that's data table 03.02 and you can see it's completely blank. The 0301 on yours may have some data in this first line. Okay, but that's the data table that I need to fill in. Let's go look at the PDF now. All right, here's the PDF file, and you can see it says Wien's Law and Stellar Spectra. The things that you're going to need for this lab are in the table at the top. That's always the case. There's the template file. That's the PDF file. That's the file that we're reading right now. You need that. There is the data file. That's the Excel file that we will upload, fill in and upload, and then the questions. And that's where we're going to answer our online questions and we're going to upload our data file. Now there's a lot of background information here. You should read that, especially the part about blackbody curves. Okay, if we zoom in on this image right here, this is a blackbody curve. And you can see on this vertical axis over here, it says energy density. You can think of that as intensity. That's the intensity of the light that this blackbody is outputting in the form of electromagnetic radiation, which would be light. So across the bottom is the wavelength in meters of the light that it's outputting. And you can see it's outputting more light right here at the top right there than it is, say, down here. It's outputting less light down here. At this peak up here, that's the place where it has the maximum intensity, and the wavelength at which it has the maximum intensity is this wavelength right here, which is a point along the bottom wavelength scale. And that point is called lambda max. So the lambda max is the wavelength of the peak intensity. And the interesting thing about black bodies is if you heat them up, they have different lambda max values. For example, in this curve right here, you can see this is a 3000 Kelvin black body. It's emitting right at that wavelength right there. That's its lambda max. And that's somewhere outside the visible range. I don't know if you can see this very clearly, but the visible range is from there to there. To the left of that is the ultraviolet. To the right of that is the infrared. So this is outside of the visible region. The lambda max for that 3000 K black body is outside the visible region. However, the 4000 K black body is somewhere inside the visible region, and then the 5000 K black body is somewhere also in the visible region, somewhere around probably yellow. 4000 K may be somewhere in the deep red. Okay, so there is a relationship between that lambda max value and the temperature. You'll notice the lambda max shifts to the left as the temperature increases. And also, there's more intensity of the radiation at 5,000 K than there is down here at 3,000 K. Okay, so the relationship between lambda max and the temperature is given by this equation right here. And you can see lambda max is equal to 2,900,000 divided by T. Now, if you were going to solve for T out of this, you would just change places with the lambda max. So T equals 2,900,000 divided by lambda max. That's the way the algebra would work out. You just exchange places with the lambda max and the T, and you'll need to do that for part of this lab. Now, it talks about in the background information, it talks about conversions. The wavelength we need to enter it in nanometers. So this lambda max is going to be in nanometers. And if we do that, then this is the correct equation. Everything works out. The temperature will be in Kelvin. Okay, now these curves back here, these are for perfect black body curves. So these are theoretical in nature. Any object that gets heated up is going to have a curve similar to this, but it's not going to be as pretty as these curves because reality is never as perfect as these theoretical curves. So a star is a close approximator to a black body. And if you look at, this is once again a plot of intensity on the vertical axis and then wavelength on the horizontal axis. The difference here is the wavelength is in units of angstroms. Can you see that right there? That is the unit, and it says A, and it's got a little circle over the top. That means angstrom. Now, angstrom is a length measurement that is 10 times 10 to the negative 10th meters, whereas nanometers is 10 to the negative 9th meters. So this is 4,000 angstroms. Also, that would be 400 nanometers. So you just move the decimal place over 1 to convert to nanometers from angstroms. This would be 500 nanometers, 6,000 angstroms would be 600 nanometers, and so forth. Okay, well, if you look at this curve right here, this is just the visible region, a little bit of infrared over here on the right-hand side, but this is mostly the visible region of a spectra of an actual star. So this is real data. And you'll notice there is a shape here that looks kind of like a portion of one of those blackbody curves. You'll notice it goes up like that, and then it reaches its max, and then it comes back down like that. Okay, so it's just a portion of one of those blackbody curves, and it has a lambda max somewhere right around here, and that's just an estimate. Now, what you're going to do for this lab is you're going to estimate where you think lambda max should be. Now, there is an acceptable range over which the answers are considered correct, but there is no absolutely right answer for this. As long as you get within a range that's somewhere right around there, which makes it somewhere right around here as far as wavelength goes, then that's an acceptable answer. But if you guess, oh, it's over here, no, that's wrong. It's wrong for this one anyway. Okay, so now a star that has a temperature, a surface temperature, between 2400 and 3700 Kelvin is considered an M-class star. If the temperature range is between 3700 and 5200, it's K. You can see 5200 to 6000 G, 6000 to 7500 F, 7500 to 10,000 A, 10,000 to 30,000 B, and then anything above 30,000 is considered an O-type star. So these are the spectral classes of the stars, and they really are indicators of temperature. So it's O, B, A, F, G, K, M. Those are the spectral classes, and that order is something you should know. So a good mnemonic device to remember that is given in the textbook. But my favorite is, oh boy, astronomy final's gonna kill me. Okay. All right, let's go down here and look at the procedure now. Step 1, we're going to begin by inspecting the SDSS data. The SDSS stands for the Sloan Deep Sky Survey. That's an actual data repository of images that we're going to use for this lab. And those images are at the bottom of the lab. So let's scroll all the way to the bottom here, past everything, and here are the images. Here's the first image, and you can see for this image I've already drawn what I estimate is a smooth curve through it so that I can estimate where I think lambda max is. Lambda max looks like it's going to be right around there. Okay, so what is that? That's about, let's see, this is 6,000. Over here to the right is 7,000. Now that's 6,000, 7,000 angstroms. And it looks like lambda max falls right around, I'm going to guess, there. I'll say that's about 6,200 angstroms. So that's 620 nanometers. Okay. And beneath that is the next one, and you can see, okay, here's the general shape of the blackbody curve. This one, it's a little more rugged, but you can see that it does have a higher level over here, and then it kind of smooths out and drops down to the right. So again, that's just a region, a small region of the blackbody curve. And you're estimating where that should be. When you do your estimates, you should probably ignore these deep dips. Just continue on through maybe something like that. Okay. All right. You can see it rises up on the left-hand side here, and then it falls down as you go farther towards the right. And again, ignore these deep lines here. Those are absorption lines. But you may ignore those and just go by the top smooth, where you think the curve should be if it were a perfect black body. Here's another one. Not as high, not as large of an intensity, but it does have a peak, and it looks like the peak's going to be somewhere right around in this region, in my opinion. Okay, but your opinion can be different. Again, here is another one. Another one. Looks like it has a peak really far over here to the left-hand side. And another one. Again, ignore the deep dips and just go by the smooth portion on top. There's about 10 or 13 of them. Okay, now let's go back up and look again at the procedure. Step 1 of the procedure is inspect the data, which we just did. Step 2 is imagine a smooth curve through the data. And then if you need to, you can print these out. An example of that smooth curve is the one that I showed you for H5309. And then step 3, envisioning the smooth curve, which you may want to draw on a printout if you want to go that far, then estimate the peak wavelength. So figure out where lambda max is for each of the curves. Then convert the lambda max from angstroms into nanometers. And remember, the way to do that is just to take one decimal place off of it. So 6,200 angstroms is 620 nanometers. That's really straightforward. And then you're going to record the value of lambda max in the data table, in data table 03.01, which will be the Excel file for the online students. You're going to need to turn in the Excel file to get any credit for this lab. Okay, and then step 5, take that peak wavelength in nanometers and use the equation that we saw and convert that into a temperature. And when you do that for this, it's 4677 K. So in step 6, what we're going to do is we're going to record that temperature in the table in step 5, but in step 6, we're going to now determine what the spectral class is. So for step 6, we need to go back to that table that you saw back here. We need to take this table, and based upon what the temperature estimate was that we calculated, we'll determine what the spectral class is for the star. And we'll also record that in the data table. After we do that for all of the stars here in data table 1, then the instructions are to sort data table 1 to create data table 2. So we want the hottest star up here at the top and the coldest star down here at the bottom. So we need to arrange the stars in order of decreasing temperature from hottest to coldest. And after that, we're pretty much done, except we need to answer the follow-up questions. So looks like there's 5 follow-up questions, and then you will also upload your data file. Okay, so let's step through the very first one here. Now, it's already done here in a data table 1 for us, so you can see what my estimates were. But let's go through those steps so that we can fill in the Excel spreadsheet. So this is the first star. This is H5309, and you can see it's got the smooth curve already drawn through it. And my estimate for where the peak ought to be is somewhere right around there. And it looks like that should be, let's say it's right at 6,200 6,200 angstroms. So I'm going to go over to my Excel file now. And now that I'm back here in the Excel file, I'm going to enter in not 6,200, but I'm going to move the decimal place 620. So now it's in units of nanometers. Then I'm going to use the equation to determine what the temperature is based upon my observation of 620 nanometers for lambda max. So let's look at that equation one more time so that we can refresh our memories. Okay, here's the equation, and you can see it's lambda max equals 2,900,000 divided by t. And like I said, just swap places with the t and the lambda max. So lambda max goes down here where t is. T goes up here where lambda max is. And again, that's the way the algebra works out. So I need to enter in 2,900,000 divided by my lambda max that I just entered. So let's go over to the spreadsheet again. And now let's use a formula to enter this in. So I'm going to type equals 2,900,000 divided by, that's the slash, this value over here, 620. And now I'm going to hit enter, but look at what I entered. It's equals, that tells Excel that it's going to be a formula. So equals 2,900,000, so there's 5 zeros there, and then divided by B2. B2 is the cell over here that's got the 620 in it. Now when I hit enter, there is the temperature. Now I don't need all those decimal places, so I'm going to go up here and I'm going to reduce down the number of decimal places. In fact, I don't even need any decimal places for this one, so I'm just going to call it 4677 is my temperature. Okay, now that I've got my temperature, I need to go over here and figure out what the spectral class is. Now, that is just looking at the table and determining it. So let's go back and look at the table one more time. Okay, here's the table 3.01. And what was it, 4677? Looks like 4677 is in this range right here. And it's going to be K. So I'm going to go over once again to my Excel spreadsheet, and I'm going to enter in K. Okay, so here I am back at the Excel spreadsheet. I'm going to enter in K right there. Okay, there. Now, that's it. That's all you have to do for data table 1. And you need to do that for all of the stars that are listed here. And all of these have images of the individual stars at the end of the lab template. So I'll leave it to you to fill in all of these. After you've finished this data table, you need to go fill in data table 03.02. Let me show you an easy way to do that, because remember, these columns are exactly the same. So we've got the SDSS image number or name. We've got the estimated lambda max in nanometers. We've got the temperature in Kelvin, and we've got the spectral class. So those 4 columns right there should match in order the same 4 columns that we've got over here. So here's what you can do. Just select all of these. After it's filled in, you need to do this after it's filled in. Now that I've selected those, I'm going to right click and I'm going to hit copy. Okay. Those are called marching ants because they're going around, marching around the rectangle there. Now let's come over here to 2, and I'm going to put my cursor right there, but I'm going to right click again and I'm going to enter paste. But this time I want to enter paste values. Okay, so paste values. Looks like it screwed up some formatting here, but I can fix that. Let's pull this out a little farther. There, fixed it. Now, for yours, you're going to do this after you filled in data table 03.01. So all of these blanks that show up here are actually going to be numbers that you've already filled in. And you'll notice it put the decimal places back here. I can get rid of those. But whatever you do for one, be sure you do it for all of them. And now I need to sort this from hottest to coolest. Okay, so what I'm going to do is I'm just going to enter in some numbers here. 1, 2, 3. Oops, those should be numbers, not letters. Just going to enter in some numbers, some stupid numbers. I'm just making things up. Okay, now yours would have actual data in here, but I'm going to sort by the temperature, and I'm going to do that by selecting just the data portion. I did not select the headers, did not select this first column over here. And then I'm going to go up to sort, and I'm going to sort by column D. Column D is the temperature, and I'm going to sort it from largest to smallest. So let's do that and see what happens. There. It sorted it. This is the highest temperature. This is the largest number. And then the smallest number would be down here. But you also notice it sorted all of the columns that I had selected. So it put the H5309 right here in the middle somewhere. Okay, but that's just an easy way for you to do the sort. And be sure you follow those instructions. Be sure to paste just the values and then do the sort according to the column. And then after I've done that, I could get rid of those decimal places one more time if I want to. That's under the Home tab, Numbers, and let's get rid of them like that. So it's displaying 0 decimal places for this. Okay, we have completed that. Then the next thing we need to do is we need to upload our data file, and we need to answer the follow-up questions. Now those follow-up questions are down here towards the bottom. Here they are. And I'll leave it up to you to do these and to upload your file. Now be sure on your Excel file that you have saved it to a place that you know. Look at the file before you upload it and then upload it. Now these quizzes are set up in such a way that anytime you start a new attempt, it wipes out your old attempt, and I really cannot see it without going through a lot of trouble. So when it wipes out your old attempt, be sure that you answer all of the questions and do the file upload one more time, because when I download these files, it only gives me the latest attempt. Okay, so we walked through the Wien's Law Lab. Hopefully that's helpful to you. Let me know if you have any questions, and I'll see you online.